Good day. Today I'm going to discuss about the mechanical behaviours of materials. Here's the content of today's topic. Definition of mechanical behaviour. Different types of loading. What is elasticity? Different types of elasticity. And importance of the topic. Now let's proceed. What is mechanical behaviour may be defined as those which affect the behaviour of the agricultural material under the applied force. Such properties include stress-strain behaviour of material under static and dynamic loading, flow characteristics of material in air or in water. When the action of forces result in deformation and flow in the material, the mechanical property is referred to as rheological property. Here's the different types of mechanical behaviours. Bending stress occurs when a material is subjected to a bending load or force. Tensile stress is a stress resulting from forces directed away from the sample. Stretching a rubber band produces tensile stress in the band. Compressive stress is a stress resulting from forces directed at the sample and acting to push on or compress it. Torsional stress is that shear stress exerted on the sample resulting from a twisting action. What is elasticity?
Elasticity is the capacity of a material for taking elastic or recoverable deformation. It is the point below the linear limit. Deformation from the bio-yield point to the point of rupture is not all recoverable. The unrecoverable part can be taken as a measure of plastic deformation.
Here are the types of elasticity. Linear elasticity is the property of a material to become deformed due to certain loading conditions without yielding. Just think of a rubber band. It is a perfect example for linear elasticity. Here's a diagram for how proportionate rubber band with its stress and strain when subjected to tensile stress.
Next is nonlinear elasticity. Refers to the behavior of materials that deviate from hooks when subjected to large deformations. Here's the example. Sponges exhibit nonlinear elasticity due to their unique molecular structure and the strain energy density function that governs their behavior. Unlike linear elastic materials, sponges can withstand large deformations while still returning to their original shape when the load is removed. In the context of nonlinear elasticity, the relationship between stress and strain is more intricate than in linear elastic materials. Unlike linear materials, where stress and strain have a simple linear correlation, nonlinear materials exhibit a strain-dependent stress response. As strain increases, the stress behavior becomes more complex due to factors like material softening, hysteresis, and energy dissipation. Essentially, the stress-strain curve for nonlinear materials is not a straight line, but rather a more intricate path that reflects the material's unique properties and behavior under deformation.
Next is inelastic. When stress exceeds a certain point, called the elastic limit, materials may undergo permanent deformation. Plastic deformation occurs when the material doesn't return to its original shape after the stress is removed. Here's the example for inelastic. Clay is considered inelastic because it lacks the ability to regain its shape after deformation. When wetted with the proper amount of water, clay forms a cohesive mass and retains its molded shape, but it does not exhibit elasticity like rubber or other materials. Unlike perfectly elastic collisions, where no kinetic energy is lost, clay collisions involve energy transfer to other forms, such as thermal energy or material deformation, due to its inherent inelastic behavior. In the inelastic region of a stress-strain diagram, the relationship between stress and strain is no longer linear or proportional. This is the region where the material has surpassed its elastic limit and permanent deformation begins to occur. Even when the stress is removed, the material does not return to its original shape or size. This behavior is significantly different from the elastic region, where stress and strain are proportional, and the material returns to its original state when the stress is removed. The inelastic behavior is crucial in understanding the ductility and toughness of materials, which are key factors in many engineering applications.
Understanding the stress, strain, force, deformation, characteristics of agricultural materials is important in designing, processing, and handling equipment, and also in understanding the behavior of the material under applied force. There are a number of tests used to determine the behavior of material for a given type of deformation and given type of loading pattern. The Universal Testing Machine, UTM, and the triaxial machines are some of the machines used to test the mechanical properties of materials. This is stress-strain curve, which is used in materials science to describe the behavior of materials under mechanical load. The horizontal axis represents strain, which is the deformation or displacement of material per unit length. The vertical axis represents stress, which is the force applied to a material over its cross-sectional area. This curve typically shows how a material reacts to stress, indicating its elastic and plastic deformation regions. The solid line indicates the initial loading path, where the material deforms elastically and then plastically before reaching its ultimate strength, the highest point on the curve. The dashed line likely represents unloading, showing that when the force is removed, some permanent strain remains in the material. This type of diagram is relevant for understanding material properties, such as elasticity, yield strength, and tensile strength. Proportional limit. From the origin to the point is called proportional limit, where the stress is directly proportional to strain. The elastic limit is the limit beyond which the material will no longer go back to its original shape when load is removed. Yield point is the point at which the material will have an appreciable elongation or yielding without any increase in load. The maximum ordinate in the stress-strain diagram is the ultimate strength or tensile strength. Actual rupture strength. Rupture strength is the strength of the material at rupture, also known as breaking point. Here's some common terminologies commonly used on mechanical properties.
Thank you for watching.